Greetings all, this is Group 15 and this is our portfolio of evidence for brownfields. First things first, I would like to introduce the team. We have Bradley, we have Sakile, we have Ngobile, we have Kuselo and myself, Mpo. So the agenda for this presentation is to present our portfolio of evidence for brownfields, which is divided into 6 sections. The first section is the software development source file, which will be presented by me. The second section is the code and design, which will be presented by Bradley. The third section is the database management system, which will be presented by Kuselo. The fourth section is the testing, which will be presented by Kuselo. The fifth section is the SQL implementation and data management in a web application, which will be presented by Sakile. And the last section is the documentation, consistency, and design, which will be presented by Ngobile. So, what is Brownfields? Brownfields is a project whereby we had to work on an existing code base, which is Robot World. We had to refactor and fix the errors, and also we had to add new features to the project. We used GitLab as our collaboration tool, making it easy for us as a team to track and manage all the code changes that were made amongst ourselves. We also implemented Docker for our project. We implemented a CI/CD pipeline. We also implemented an API and a database, and we also made sure that we run our project through CodeScene to check our code health. We made use of Git issues, making it easy for us as a team to track all the progress that we made. Let's say, for an example, we had to add a test to save the world. So we would create an issue for that, and every time when we are done, we would close that issue. And this is how our project is structured in GitLab. So we have our YML file, which is the pipeline file, and also we have the README. Inside the robot world file, we have the SRC file, which contains the main file and the test file, and also we have our Docker file, the make file, the prom file, and also the bash script. Inside our SRC file, as I mentioned, that it is the main file and also the test file. And inside our main file, this is how we divided our different section. So we have a folder for an API, a folder for a client, a folder for database, a folder for server. So basically, anything that has to do with the API, it is under the API folder. Anything with the client, under the client folder. Anything with database, is under database, as well as the server. And under our testing, this is how our testing folder looks. So we divided all the testing. So we have a testing for our API, we have a testing for our acceptance test, and we have the server and the client unit test. Right now, I will hand it over to Bradley to present our code and design.
Okay, beginning with section B, code design and alignment. So in any project, the adherence to given specifications is crucial to ensure that the project meets all the intended requirements. So to demonstrate that our code has been created to adhere to these requirements, I'll take you through our application. But let's start with this slideshow, which is just a reference of everything that we'll be going through today. So specifications outlined in the project, the good use of programming conventions, the methods of accessing data, conformity of design, testing, demonstration of testing, user experience, and yes, user experience continued, the installation of our project, description of our project's purpose, the documentation regarding the layout, programmer friendliness, and yes, so let's go back to the very first slide. So what we'll be going through in this first part is taking you through our application, starting with the GitLab. Let me take you through our GitLab issue board. So every issue that we've worked on in the project started here in the issues board, ensuring that everybody in the team always knew what they were working on and what had to be achieved. So if you look at any issue on the issue board, you'll see that the issue started with a story, ensuring that every scenario was accounted for. So we can see for this one, for example, our launch scenario 1A, we see that we have a story here that given that I've connected successfully to the server and launched my robot, and I've launched into a random position. When you type a moving command, assuming that there are no obstacles in front of you, then you should get a valid response and your position should be updated. So this is the format that we worked on throughout our project. Every issue has a story. You can check any issue we see. For state, given that you're connected to a robot world server and you send a request with the command state, then you should get a valid response from the server. And yes, so we also have this for counter scenarios where a user types in an invalid command or see invalid commands or the robot is not launched. So this helped us ensure that every scenario in our project was accounted for. So this was the first part of us adhering to the specifications of the project, which was to ensure that the tests that we wrote here that work against the reference server provided to us also work against our own. Okay, so when you clone our project, you'll be greeted with this. So our README, which is just a basic outline of how to run our client, how to execute our server, how to play the available commands, but we'll be go through this later. So let's carry on to the testing part. So this is our testing suite. We have our acceptance test, our client test, server test, and web API test. So earlier on I showed you on the GitLab issue board our acceptance test stories. So you can see here we have a number of acceptance tests for launching with obstacles, our initial launch robot test, the look robot test, move robot test, and our state robot test. So if we can open any of these classes, for example, we can see that we have tests for no space left in the world, where we have our story from our GitLab issue board that if we launch 2 robots and there's no space in the world, we should receive an error, no more space in the world. A valid launch should succeed. We type launch, we specify the robot type, shields and shots, and since it's valid, we're expecting an OK. Response invalid. We can see that we typed launch wrong. Even though everything else is right, we should get an error response of unsupported command. And these are the type of tests that we wrote to ensure that our server was compliant with the results that we were supposed to receive back. So the whole point of this was ensuring that the acceptance test that we wrote for the reference server would produce the same result on our server that we got given. Our second part is the database test. So we have our restore world test, the robot world database test, and the save world test. So see, we save a world with these arguments of size 10 and an obstacle at 0 and 8. And it should be inside the table. Our robot world database tests. Yes, and then The last test that we have are the web API tests. So we can see here, we're testing the web API. We create data in the memory. So we create test world 1 that's size 5 at an obstacle 1 1 2 1, and we send a request out here to get the world name of test world 1, and we're okay. So the second part of ensuring our compliance with the specifications was creating the makefile, which is a requirement we had to do. So in the makefile, okay, so these are just our variables: Maven, start server, stop server, the version, and the Docker. So what our project, the makefile, does is it runs our server, it compiles, verifies, tests, and then stops the server. This is just an install EOD, so we can install the EOD dependency if it is missing. So going through compile, we Maven compile, verify, we run the jar and set a timer of 2 seconds to sleep, test, stop the server, package, and this is our release part along with our Docker, and just cleaning, so deleting the target directory. Going from that, we have our pipeline. So in our pipeline, we version our Docker. So here we are compiling, we echo compiling, go to the project directory, compile, inside our tests, we print testing, go into the project directory, start the server, test, and when it's finished, we kill the server, package, we package, go into the project directory, run the job. Okay, now that we're back at our project, we can see the pipeline is successful. When we push, we can just have a look at this. So compilation, it prints where we are here. We start the Docker image, we add Maven, we'll echo, it'll download everything needed for Maven and compile the project. Go back to the testing stage and see. Does the same thing, does everything it needs to do, and here you can see it starts our tests right here, sends every test out, ensures everything works, and there we can see 19 test runs, 0 failures. We kill the server and the job is successful. To the third stage of packaging, you can see the same exact process. It packages, builds success, we kill the server and the job is successful. And the last part is releasing. So we can see that it does the whole Docker imaging process, and we push to our repository. So I can show you here our deploy, our container registry. We can see all of our image. And now to move on to the second section, which is good conventions. I'll be taking you through the class names, variable names, and just general usage of good programming practice and conventions. So you're able to see that each of our files are named clearly. So we have our API, client, database, and server. Inside of our API package, we have the API handler, inside client, we have another package, client helpers, which is the request, and the client handler, the client, the robot world client, and the robot world JSON client. We also have our client, the robot world client, and in our database, we have our database connect, the app, robot world database, and the DAO for the database. Inside our server, we have a sub package called server helpers. Each has a package for the commands. You see the commands are clearly named: back command, command fire, forward command, left command look, right command turn command. We have our headers, the obstacles, response, robots, robot models, server handler, and the world. So everything is clearly named, and this also goes for our tests. Each of the test classes are named properly. So let me just minimize all of these. Inside of our test, you see our acceptance test package, client server, web API, back command test. So we did follow good conventions throughout. We can check an example, a test. See that everything is formed correctly. Test fire command test. We follow the camel. So now let me take you through the methods of accessing data in our program. We have our DB classes, the database itself, and the web API. So we can just go here, back to our project. So our database class is how we access, how we save and retrieve information about the world from from our database table, our worlds table. You see we have our read data, get world by name, get all saved worlds. So here we have our getters and setters. So get world name, set world name, get the size of the world, set the size, get the obstacles and set the obstacles. This is just our DAO that we use to query the table. So our web API also does this. So we have two get requests, so we can get the world by the world name, which is the world in general. So our API handler, you see here, we use our database to get the world by name, and we pass in the connection parameter and the world name and get all worlds. So this is how we get the data through our project, how we can see the name of the world. Excuse me. Okay, so in this section, we'll be going over user experience and demoing our server application and client. So let me switch over to Visual Studio Code so you're able to see what I'm talking about. Let me go to let me run our server. So we see our server greets us friendly. Say welcome to the robot world. We have a new robot world, and it says the size each robot can see in this view radius. So let me just say, so if the user is unfamiliar with the commands, the server tells them type view for available commands. So if you type view, you're able to see the server commands of quit, robot, view, and dump. So quit will obviously shut down the server. Let's run the robots command. There are no robots connected. And if we dump, it's going to show the number of robots in the world 0. There are no obstacles, and the size of the world is 1. So let's just quit to show you that it works. So quit, and the server shut down. So let me start the server up again, and I can show you the client side. So client, if you run this, it's going to show you. Welcome to Robot World. Get started. Choose your robot character. So we have Blaze, Demolisher, Reaper, Venom, and Warpath. The icons aren't showing because I'm not on IntelliJ, so it doesn't support the glyphs that we used inside here, but it shows the amount of shields and shots that the robot has. So even if the user is unfamiliar, it says launch Reaper James, for example, so it would be the robot type and the robot name. So we can launch Venom Sita. Now we see result is okay. We show our position, the direction we face, the shields, and our shots. So if we go back to the server, we can see Sita joined the game at position 00, and now we're able to see. If we type view again, now we can run the robots command, and now we can see there's a robot named Sita at position 00, shields 20, shots 16. And if we dump, now we can see bot Sita is at 00 facing north. There's now 1. Okay, so the next part of this is installing everything needed for our project to work. So if we go back to our project, you can see every dependency needed for our project to run is in this POM file. So the user does not have to install anything external. Running mvn clean install inside the project will suffice for all the dependencies to be installed, and the project will function as intended. So now let's go back to our PowerPoint. Next part is description of our project's purpose. So I'll take you through the README. So here in our README, the user's greeting. Welcome to the amazing robot world. Explore a virtual realm where robots roam freely amidst towering mountains, shimmering lakes, and mysterious bottomless pits. Embark on an adventure where every command you issue shapes the destiny of these mechanical marvels. Are you ready to unleash your creativity and command robots in this dynamic and interactive simulation? So we go to the setup, which is running the server. So this is the initial thing that needs to run. So if we navigate to our directory, we execute run server.sh, which is right here. We run the client next to connect the client, and here just instructions on for the client on how to play. So launch robot model, robot name. Start the game by launching a robot into the world with a unique name. The commands, so the available commands are forward with a number of steps, back with a number of steps, turn left, turn right, look, fire, reload, and repair. And it is just engaging on what those comments can do. So exploring the world using look to scan for information about nearby obstacles, other robots, and potential threats. Engaging in combat, so fire. Strategically using the fire command to disable other robots and gain a tactical advantage in the game. And winning, so the whole objective of the game is to navigate your robot successfully through the world, avoid obstacles, engage effectively in combat, and achieve dominance to win the game. So basically killing every other robot without dying yourself. So we can only move forward, back, left, right, and looking fire. The different types of obstacles you may encounter: mountains, lakes, and bottomless pits. Okay, the last two parts of our project are now the documentation of the layout and the programmer friendliness, so our fellow programmers would easily read our code. So let me go back to our IDE. So the project is laid out clearly, you can see. So here Inside our source file, we have every package labeled, given a clear name. So API, client, database, server. Inside all of these, we have our request where there's documentation talking about exactly what this method does, the getters and setters, what this method does. And each of the methods have clear and descriptive names. You can see we have all of these, so it's not a mission for whoever's working on this to understand what it does. And the ones that don't have any documentation are pretty self-explanatory pieces of code. But generally, most stuff that could cause confusion, we do have documented. So as for the layout, everything is laid out pretty nicely. It's in its own respective package. So everything that is of a certain command is with the commands, obstacles are with the obstacles, responses are with the responses. Everything to do with the robots are with their other robots. The robot models are in their own package. Server stuff are with other server stuff, in the world and config are both together. So that is how our project is laid out and how it's easily understandable for any other developers that might work on this or just want to have a look at the code.
Okay, now we are going to talk about data management systems, a comprehensive overview. Data management systems, or DBMSs, are crucial for effective organization, storage, and retrieval of data. They are a backbone of modern applications and play a vital role in various industries, from e-commerce to healthcare. This presentation will delve into the intricacies of DBMS, exploring their features, types, and the impact they have on data management. We will examine the problems related to data management and how DBMSs address them effectively. Data management challenges and their roles of DBMSs. Data management involves organizing, storing, and retrieving information effectively. It plays a crucial role in many industries, from e-commerce to healthcare, as we said. However, traditional methods often face challenges such as redundancy, inconsistency, security risk, and integrity issues. Data redundancy refers or arises when the same data is stored in multiple locations, leading into inconsistencies and wasted storage. It can also create challenges for data integrity and maintenance. Data inconsistency refers to when data is duplicated, different copies may be updated independently, resulting in inconsistencies. This can lead to inaccurate information and unreliable decision making. Data security is a crucial concern, especially with sensitive information. DBMSs provide mechanisms to control access, enforce permissions, and to protect data from unauthorized access or manipulation. Data integrity refers to the accuracy, consistency, and validity of data. DBMSs employ features like constraint, triggers, and transactions to ensure data integrity and prevent errors. Then we have DBMS features. These include DDL, DML, and DCL. Data Defining Language, or DDL, allows users to create, modify, and drop databases objects such as tables, columns, indices, and relationships between tables. DDL is essential for establishing the schema of a database, which dictates how data is organized and stored. Then Data Manipulation Language, or DML, enables users to interact with data by performing operations such as inserting, updating, deleting, or retrieving data. It provides a standardized interface for accessing and manipulating database content. Then we have Data Control Language, DCL grants and revokes access privileges to data objects, ensuring data security, controlling user access to sensitive information. It enables granular control over who accesses or modifies the data. Then we have types of database management systems. These include relational databases which store information in tables with rows and columns organized using relationships. Examples include MySQL, Postgres, and Oracle. They are widely used due to their flexibility, scalability, and robust features. Then we have hierarchical DBMSs. These structure data in a tree-like hierarchy with parent-child relationships. These models is suitable for data with clear relationships, such as family trees or organizational structures. They include informational management systems. Then we have network DBMSs, which allow more complex relationships than hierarchical ones, which record potentially having multiple parent-child records. They are suitable for data with intricate relationships such as airline reservation systems. Then lastly, we have object-oriented DBMs. They store our data as objects which encapsulate data and methods. They are suitable for complex multimedia or object-oriented applications. Examples include object store, system tools. These include SQL query builders, which allow users to construct SQL queries through drag-and-drop interface. This simplifies complex query constructions and helps prevent syntax errors. But their limitations are flexibility compared to just writing raw SQL. Then the second tool is data visualization tools. They present database data in a graphical charts and dashboard for better understanding. Their limitations may require additional skills to interpret complex visualizations. Then we have backup and export options. Backup and export options. These backup the database or export data to various formats such as CSVs, JSON, or SQL script. These simplify data sharing and archiving, but their limitations may be that end-user tools might struggle with very large databases due to file size limits or memory constraints. Then we go to the reasons why we chose SQL3 in our application or in our Robo 12. The project required a lightweight and a self-contained database, which SQL gives us that, since we can just, it is a one-file system. It also has 0 configurations you don't need to install, and it can be it can be used in cross-platform capabilities such as Linux, or you can also use it on Windows and other platforms. It has a small size, or it can be used in small size to medium applications, such as our application, which is Robot World. Data access objectives that made us choose SQL3 is because of their ease of use. It has 0 config setups, making it easy for developers to integrate and use within the application. It is portable, easily moved between different environments, crucial for development and deployment flexibility. Also, the crucial performance factors include low resource usage. We are able to run effectively on systems with limited resources, making it suitable for embedded system or mobile application. We can back up and recover. It is simple to copy and recover the database in case of corruption or file damage. Okay, now we are going to go to the database design and implementation. Database design, we created a table with a schema which reflects the requirements of our project. These include defining the tables, columns, and data types. I'm going to show you after this slide. Then the normal database tables reduce redundancy, improve data integrity, since we also have a constraint that allows us to not have multiple wells with the same name. Then we also are able to connect to the database, implement to establish connection between the database and our application. We use the ORM to do that. Okay. We have the whole name and the size and the obstacles. These are the columns we have in our database. Queries to get the information, we have the select queries for selecting the world by their name, which is it will return the world name, size, and obstacles from world where the world size is or the world name is specified. Then we have another query, which is a select query again, which now will list all the worlds that we have saved in our database. We can also update our world using the insert query, which will take in the world name, the size, and the obstacles.
Sakile Mlambo, and on this section, I'll be speaking about evaluating SQL implementations in the Robot World project. SQL is short for Structured Query Language, which is a standard language used to interact with relational databases, enabling the storage, retrieval, manipulation, and management of data within our Robot Worlds environment. In the Robot Worlds project, a database is essential for maintaining the state of the world, managing the robot's configurations, storing obstacles, positions, and preserving the world across different sessions. Without SQL, the persistence of the state, robot data, and user interactions would be impossible, making it critical to the dynamic and interactive nature of the robot worlds. The objectives of this presentation, it is aimed to explore the role of SQL within the architecture of the Robot Worlds project, focusing on how it is used to manage the world data. We'll also examine how SQL queries are implemented in the project, how they contribute to the data integrity and performance, and how they enable the seamless integration between different components of the simulation. Additionally, we'll also discuss how SQL connects the back-end database with the front-end simulation interface, ensuring that all data flows smoothly and efficiently. The database is central to Robot Worlds, managing all persistent data, including robot configurations, world state, obstacles, and user commands. This data is critical for ensuring that the robot worlds can be saved, modified, and restored, allowing for continuous interaction should there be any disconnections. The database schema overview. The database consists of several key tables, including worlds, robots, obstacles, and commands. The worlds table stores information about different simulation environments, including the size and unique identifiers. The robots table include data such as robot IDs, positions, orientation, and statuses. The obstacles table captures details about obstacles in the world, including their types and positions. The commands table logs the history of actions executed by robots, helping in debugging and analysis of robots' behavior. The relationship between these tables ensure that the world is accurately represented, and can be efficiently manipulated. Here's a quick overview of four SQL queries. For example, we have insert, right? So for insert, we can insert into robots. So we'll have to list an ID, position, and orientation. An example would be ID 1, position 0 is to 0, and the orientation would be north, meaning that we'll be inserting a robot with an initial position at the center of the world. We also have select. For example, if we can run the query select from obstacles where the ID is 1, and when we select from there, we'll be able to retrieve all obstacles in that specific world. We also have the query update, and we can run update robots, and then we can set a position of 1 is to 1 for where the ID is 1, and then this will update the position of that specific robot. And we also have, we can run the query delete, and if we run delete from world where the ID is 1, we'll be able to remove the world from the database that has an ID of 1. Integration of SQL queries into the Robot Worlds code. These SQL queries are embedded within the Robot Worlds backend logic, typically within functions that handle Robot Worlds creation, robot commands, and the state saving. For example, when a robot moves, an update query modifies its position in the database. Readability and maintainability. SQL code is structured clearly to ensure that it is readable and maintainable. Best practices such as proper formatting, use of comments, and consistent naming conventions, we have followed those to make the code easy to understand and modify by other developers. On this section of the video, I'll be going through our code base of the SQL part of our code base. As you can see, we have a package for the database and we have a class right here. So I'll go through the database connect class, right? So as you can see, what we did first was to initialize a connection by connecting to a database using a remote database with a given URL, right? And the reason why we use a URL is because we are connecting to a remote database. And the reason for connecting to a remote database is for persistence, right? So since we are using a remote database, this means that each time our code compiles and each time we deploy any new features on our code, we do not lose any previous information and the database continues to persist and adds on new information. So we also have a constructor where we are establishing the connection to the database using the URL, right? And then this is a method to establish a connection to the database as given above here where we are using the database URL, right? And on this section, we have a method that creates the world if the table doesn't exist already, basically initializing the database, right? So we have SQL commands, for example, in here. So we are going to create a table if the table world does not exist already, right? And then this table will then have worlds, right? And the worlds we will have the column worlds will have an ID. Will also have the world name, and the text on the world name should not be null, right? And we'll also have a size, and the size should be an integer, and the integer should not be null as well. And the obstacles we have decided to make them text, right? And then we've also made use of try and catch statements where we'll be able to try. So if we are establishing the connection, right, initializing the database, and that table already exists, we'll be able to print out that this table already exists. And if there's any issue, we'll be able to actually catch that error using SQL exception error handling, right? And we'll be able to print the detailed error, right? So we also have a method where we are able to insert values and data into the database. So the very first thing that's very important would be to establish the connection to the database, right? And then now we can insert these values to the columns where in the worlds column, right, we'll be able to add the world name, the size, and the obstacles, right? So these will be the three values that we are adding, right? And to reiterate that on the first index, we'll have the name of the world, right? And then we'll have on the second index the size. We'll also have the obstacles as well, right? Going down, we have another method, and this is a method where we are able to read data from the database tables, right? So right here, right, is a statement, and then on this statement we are selecting the world column, right? And on this column we are looking for these statements, the ID, right? This is what the column is labeled. We are looking for the ID, and then we also can get the world name and the size, as you have seen previously when we were creating the columns, and we also will be getting the obstacles, right? So since we are using this method to read data from the database, right, we are also able to update the server settings of the retrieved data. On this section of the video, I'll be going through our another method we have is to retrieve a world by its name, right? So after establishing a connection, we are going to run the SQL query right here, right? And we're going to establish the connection. And then we are going to have a set statement. And then this set statement is going to say that we are going to set the string value of the first index to be the world name of that we are retrieving, right? So we are going to go through all the results of the worlds that we are going to receive as the database results. And then from those results, we are going to then get the world name, the size, and obstacles, but we are only going to return that world. Since we have set this statement, that means we are going to get the name of the world, right? And then on this one, this method, we are going to retrieve all the wells that are saved in the database, not specifically by their names, right? So after establishing the connection again, we are going to initialize a list and then run our database query. So in this case, from the results, from the database, we want to select from the column of wells, right? And right here, we are going to get all the results. And on the results that we are getting, we are going to iterate through all the results. And for each result that we are going to get, we are going to add the world into the list that we have initialized, and we are going to return all the worlds that we have found in our database inquiry as a result. Another method we have is to retrieve.
Now we can go to the section of testing, which will just be about me showing you all the tests in our project more in detail. The acceptance test, database test, and the web API test, as well as the usage of our makefile to automate testing, as well as the pipeline and how it automates testing. So now let me just switch over so I can show you the tests. So here are our tests. So we have multiple test suites. So our acceptance test covers various scenarios. So launch robot test. So in each of our tests, before each test runs, we connect to the server with the port and the IP. And after each test is run, we disconnect from the server. So we have multiple tests. So valid launch should succeed, invalid launch should fail. Can launch another robot into the world. Launch 9 robots without an obstacle. Launch robots with an obstacle in the world. So now we have here for 2x2 world, launching a robot. Our initial suite of launch robot tests with no space left in the world. Valid launch should succeed, invalid launch should fail, and the same name is connected. Look robot test, so we have valid look command, invalid look command, robot sees an obstacle, robot sees another robot and an obstacle, as well as look in empty world. Move robot test, so we have our move forward at the edge of the world, move back at the edge of the world. And sorry, let me just go to state robot test. We have the state of an invalid robot, state of an existing robot. Our restore world test, this is for our database. We see if a world can be restored. And then here's just checking if a database can be initialized, saving the state of the world. And our web API tests, we have here, we just create a database in memory and populate it with 2 worlds, and we're testing the values of those 2 worlds. So getting the valid world name, invalid world name, and then just getting world. So I can just show you our makefile, how that automates the testing process, and just clear and run our make call. We start our server, compiles the project, verifies. Now it runs the tests. No test fail. Now testing again. Build our project and the reference server stops. Everything works. Let me just show you our database test now of Save World. We run our test. See, the test of save command works. We run our database tests. They all work too. And let me just go to our web API testing and run that. And all three of these methods, yes, test pass. Same goes for our server.
Hi everyone, welcome to our presentation on evaluating documentation consistency and design adherence in brownfields projects. Today we'll be walking you through our journey, the challenges we faced, and how we ensured our project documentation aligned with the design and the actual code base. Our project involved working on an existing codebase called Robot World. The main challenge was to improve and add new features without disrupting the current system. This is a classic example of a brownfields project where we focus on modifying and extending an existing system rather than starting from scratch. Okay, coming on to the next slide. One of the key challenges was maintaining consistent and accurate documentation. We created detailed documentation for all new features and changes, ensuring they aligned with both the original design and the actual code implementation. This was crucial for keeping the project manageable and understandable for all team members. Facing the documentation challenge in our brownfields project required not only a structured approach, but also the right tools to ensure accuracy, consistency, and alignment with our design specification. So I'm about to take you through the tools and steps we used for the documentation challenge. Git was the main source to manage and track changes in our documentation, and also to track changes, to collaborate efficiently, and also to event changes if necessary. The other tool we used was Miro for visual collaboration to enhance our documentation process and to also improve collaboration. These tools allowed us to maintain accuracy and ensure consistency and align our documentation with our design specifications. This comprehensive approach has been crucial in supporting both the current and future success of our project. As we developed new features and modifications, we took a proactive approach to ensuring code quality. First, we created comprehensive acceptance tests for each new feature and modification. This ensured that the code met all requirements and functioned as expected. Second, we utilized CodeSeam to monitor code health. This tool helped us identify potential issues and measure various code quality metrics, giving us a clear picture of our code's maintainability and performance. By combining acceptance tests and CodeSeam analysis, we maintained high code quality and addressed problems early on. This approach allowed us to catch and fix issues before they impacted our project success. By prioritizing code quality, we ensured a solid foundation for our project's long-term success. Now let's talk about the biggest challenge we faced. Managing the Docker image was a real headache. And running our tests through the existing server required us to be extremely cautious. This challenge taught us a lot about working with legacy systems and the importance of thorough testing. Our approach to fix these errors, we used continuous integration to test code with every update and encouraged team collaboration. We held regular stand-ups and knowledge-sharing sessions to keep everyone aligned and informed. By standardizing our Docker process, improving code quality and automated testing, and fostering team collaborations, we managed these challenges effectively. To manage our tasks effectively, we divided into pairs of code pairing. This allowed us to tackle different parts of the project simultaneously, making our workflow smoother and faster. We also scheduled regular stand-ups to ensure everyone was on the same page and to address any roadblocks as a team. Another important aspect of our project was setting up a build pipeline. This automated the process of testing and deploying our changes, ensuring that we can catch errors early and maintain a consistent code base. Our pipeline automates the testing and deployment process, streamlining our development workflow. However, maintaining a green pipeline, one constantly passes all tests, has been a challenge. We encountered frequent errors, highlighting the importance of regularness, testing, and quick resolution. A well-functioning build pipeline is crucial for efficient development. It ensures consistent code quality and faster delivery, allowing us to respond quickly to changing requirements and deliver proper quality code. As we reflect on our recent Brownfields project, 3 key lessons stand out. First, clear and consistent documentation is crucial when working with complex legacy systems. Documentation is the foundation for understanding and navigating the project's information. Second, maintaining code health and a stable build pipeline requires ongoing effort and attention. It's a challenge that needs consistent monitoring to ensure smooth development. Thirdly, effective teamwork, open communication, and seeking help when needed are essential for success. Brownfields development can be complex, but together we can overcome obstacles. By embracing these lessons, we can improve our approach to brownfields development and deliver better outcomes.